So let's talk about this array of 100 16-bit size integers. So internally we know that this is the offset of this array of 16-bit integers, and basically this is the at runtime this becomes like an address of them. So right here we start storing them, and they all look like this. Basically they're stored as hexadecimal 000, and then the next one, and then the next one, and then we have 100 of them like this. If we open if we configure this build with a listing file, we should be able to actually see all of this. Now to refer to these individual 16-bit integers, and here I'm just using hexadecimal notation. This is like 2 bytes, 1 byte and another byte. So if we want to use the index, this should look like this. Of course, the first element in this array has index 0. The second element in this array will have, in a high-level programming language, this index will look like this. However, in higher-level programming language, the index is adjusted to the size of the array element automatically. Not so in assembler. In assembler, we have to basically say that, okay, this table is the address of the first 16-bit integer, but this 16-bit integer occupies 2 bytes in memory. Therefore, the next 16-bit integer is located at table plus 2 bytes. And so this is how the index will look like in our environment here in assembler environment. And so if we want, so the next one will be 4, and if I add another example right here, its index will be 6, and then 8, and then 10, and so forth. And by the way, the index of the 100th, right? So if we just try to think about the last index right here, what should be the what should be its index? Of course, again in C, its index would be 99, because it's like the size of the array minus 1. That's the way it works in C. But in assembler, because we have to account for the size of each element, is basically what we do with the simple index 0, 1, 2, 3, 4, 5, which is 0-based index. We have to essentially multiply it by the number of bytes of the data type. So here this would be index 1 has to be multiplied by 2. Index 2 has to be multiplied by 2, so we get 4. Index 3 needs to be multiplied by 2, and we get index 6. So here, of course, 99 multiplied by 2 is 198. Okay, so these are the strange ways that we need to always deal with this. Just basically remembering that each element has specific data size. If we have array of bytes, we wouldn't have to worry about this. But if we have integers which occupy multiple bytes in memory, we have to scale. We have to, what we say, we have to scale the index. And this is the idea right here. So let me give you some, let me give you just a concrete example. What if I wanted to run, what if I wanted to write code here in our program, which would set every integer in this table equal to 5. We've used 5 multiple times. So step number 1, I could potentially set, of course, I need to organize my loop. So my first step would be to set loop counter. ECX would be my choice for loop counter, and I will say, of course, I can say 100 because I have 100 elements, but remember, length of is a number of elements in the array, and the assembler knows that this is an array. This is this duplication suffix here in this allocation knows that this is an array of 100 words. So we just say length of table. Okay, so this is my counter. So I hope when we run this code, it will be set to 100. Because I need a loop, I will say, I don't know, update, or we can say init next. Okay, and so init next will be a label in this code, and loop to init next will allow me to create a loop which will basically run over here. Whatever I do in this loop will execute 100 times. So let me use the EDI, move into register EDI. I can set it equal to 0. So we can add some comments here. So this will be init counter, right? So this is the counter, and register ECX is a common choice for counting iterations of the loop, and EDI is this, we can say that init index. So then, according to what we've been discussing and knowing that this is 2 bytes in memory, if I want to update the first, first element in this array, I can say table with EDI. So this is my index, and I can move whatever I want. Move. I'll just, like I said, let's pick a specific value, hard-coded value 5. So we can say here init each element equal 5. Okay. And so we're going to repeat this. But of course, in this loop, what we need to do, we need to update the EDI. So one possibility here would be to say add EDI 2. Okay, so that should give us the desired result. So let's try this, and here what I'm going to do to test this code, first let me build. Okay, builds fine, and then I'll do this trick. I'll say debug step into, which is F11. But remember that, and I'll close this assembly window so that we have things visible. So the first thing is that I told you that this was written with the purpose of just demonstrating various syntax options. But I'd like to try my example. So I'll use this trick. You can click on the line of your source file, and then right-click and set next statement. So basically, you can reset debugger knows address of each instruction, of course. So we can ask our debugging environment to update register EIP, and by setting it here and say set next statement. Okay, so see how EIP just got updated by me simply right-clicking here and saying set next statement. So it's kind of like interesting trick that you can do in debugging environment. And so now I can run this code. But before I run this code, I will take a look at the address of my table. So debug Windows, immediate window right here, immediate window, and I will say question mark address table. So it should give me the address of my table. in my global data segment, and I will now open so I'll just copy this address from the immediate window. Again, what I'm typing is $ampersand table, so that's one of the commands that you can use in immediate window. I suggest that you actually Google Microsoft Visual Studio immediate window and learn other options that you can use in this window. It's a very nice tool to have around. So next step, debug windows. Memory, and we'll just pick one of these memory windows, and I'll just paste the address, and you can see that of course it's all zeros, right, because we initialized everything to zeros. So now let's start going through this loop to init each element equal to 5. So I'm just going to press F10, 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 and I'm just about to update the first 16-bit integer, and notice that this is how it gets updated, right? So it's stored in little Indian format, and it's so basically the lower portion of this integer. Right, the lower when we store this in memory, the lower portion is stored at the lower address. So this is why it appears as 0500. Okay, then so we're just started our loop, and I'm going to add to EDI. Oh, let me just close this. Add EDI 2. So I'm incrementing EDI. It's very trivial. It's actually incrementing it by 2, and then going back to the loop. And you see that we're jumping to update the next integer in memory, and when I do, you see that it happens. So we can actually run the entire loop by, again, just going to return instruction here and right-clicking in the source editor view and basically run to cursor, right? So if I want just to finish my loop, I can go to the next command and right-click and say run to cursor. So I run to cursor. Oh, I just actually hit the wrong key, but I just wanted to make sure that apparently what happened was that I ran and included the return instruction. So, but you can see that the entire memory block was updated. So this is one possibility, but there is another possibility to use a scaling factor, and instead of modifying, this could be getting a little bit complicated here. First of all, this hard-coded 2, maybe we can improve by saying type of the table, right? We can use another operator available here to use the type will return 2 bytes because the table is 2 bytes. But altogether, this additional computation is kind of undesirable. So one possibility here is altogether avoid this. So this would be this example would be essentially increment index with respect to the element size in memory, right? Because 2 is the size of our elements in memory. But there is one possibility here, different possibility, and this possibility is to basically scale this and multiply it by 2. Okay, so because it gets multiplied by 2, 0 multiplied by 2 is 0, 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, and then 3 by 2 is 6, and so forth. So we should get the correct index progression. And this is the possibility which x86 platform allows us to have in our indirect memory addressing, is to use scaling. Scaling is simply used on array indices to specify, to immediately specify what is the size of the element. right? And so we can do it this way, and we can even do it this way, right? So we can even use scaling like this. I don't know if it makes it more readable, but I'll just switch back to 2 just to demonstrate what kind of, like, what kind of scaling we can make. So notice that I commented this out, right? So right now this is no longer needed because the scaling should take care of it. So let's just run a very quick test of this. Build. And again, debug, step into, and once again, just scroll down to our code that we're trying to test. Right click, set next statement. Notice that EIP will be updated by the debugger. So set next statement right here. So this is the next statement. Now the next statement becomes this. And I'll just step through a few times, and before we do this, again, let's go back to immediate window and hit enter here one more time. So our global data segment got relocated to a different space, so we need to update this. It's one of the security features on Windows 10 that I'm running here. And so this is our array, the view of our array, all zeros, of course, as expected. And I'm going to continue my execution, F10, F10, F10. You can see, again, we're getting our updates. And then you can see that it just keeps updating the same first integer, because let's say debug, stop debugging. So what I meant to do here is just replace this arithmetic with this simple increment EDI, right? So the advantage of doing this is that I'm just going to use EDI as very natural index 0, 1, 2, 3, 4, 5. But I'm going to scale it, and that's the idea. Okay, so I'll just build again one more time, and we'll just run this one more time very quick. So debug, step into, and